This is your presenter, Asloob Mudassar, and I am presenting slide number 13C of the course on atomic and molecular physics. In the today's lecture, I shall be covering the following topics: anomalous Zeeman effect, splitting of states in anomalous Zeeman effect, calculation of Lande G factor for anomalous Zeeman effect. This is the third lecture in continuation of the previous two lecture in which an atom is subjected to applied external magnetic field. So this is the third lecture, and there will be one more lecture at least which will also be in continuation of this lecture. In the previous lecture, I covered the ordinary Zeeman effect, which is also known as the normal Zeeman effect. And now I am covering the anomalous Zeeman effect. Anomalous Zeeman effect. When the atomic magnetism is due to the superposition of spin and orbital magnetism, then the optical transitions between the two terms is described by both S and L, and one thus speaks of the anomalous Zeeman effect. The term anomalous is historical and is actually contradictory as the effect is normal. You see that when we talked about the ordinary Zeeman effect, I talked about their pure orbital magnetism. Pure orbital magnetism means that only orbital angular momentum capital L was present there, and the spin angular momentum was zero. Consequently, the orbital angular moment and the spin magnetic moment, the orbital magnetic moment were present in the ordinary Zeeman effect, and the spin magnetic moment, which we denote it as mu s, was absent. So only capital L, that is the angular momentum, and mu L, that is the orbital magnetic moment, were present. So only this quantity was present. That is the case was of pure orbital magnetism. And then we talked about, for the case of pure orbital magnetism, about the ordinary Zeeman effect. But now in the anomalous Zeeman effect, we shall be talking about that both spin magnetism and the orbital magnetism both are present in an atom. So when both are present, it means that the spin angular momentum capital S and the orbital angular momentum capital L are both present. And there are other relevant quantities, that is mu S, that is the spin magnetic moment, and mu L, that is the orbital magnetic moment, are present in this case. So you see that here in the anomalous Zeeman effect, we are assuming that we are considering the atoms which have both these quantities present, that is the spin magnetism and the orbital magnetism, both are present. Under the condition that when both are present, we talk about the anomalous Zeeman effect. In principle, in the beginning, when the number of lines were observed, the number of lines were not matching with those of the orbital, with those of the ordinary Zeeman effect, because the number of lines in case of the anomalous Zeeman effect were greater in number. That's why the name was given earlier to this effect as the anomalous. Anomalous mean abnormal, because at that time it appeared that this thing is abnormal, that more number of lines are appearing in this case when both spin and orbital magnetism are present, and ordinaries, and this number and these number of lines, these greater number of lines could not be explained with ordinary Zeeman effect. So that's why the name was given to this effect as anomalous. In principle, the anomalous Zeeman effect is not abnormal Zeeman effect. It is actually a normal Zeeman effect, because at that time the spin magnetism was ignored. Now, if we incorporate both spin magnetism and the orbital magnetism, then then this anomalous Zeeman effect can be explained very well, and we shall see that this is not the anomalous or the abnormal Zeeman effect, but this may be regarded as the normal Zeeman effect. But here, following the historical nomenclature, we shall call this as the anomalous Zeeman effect. But you must remember that in the anomalous Zeeman effect, we shall be talking about we shall be talking about that both spin magnetism and the orbital magnetism are present. The two terms have different G factors. Now you see that if we are considering the transition between two levels or between the two states in the anomalous case, then of course the G factor will be different for the lower state and the G factor will be different for the higher states. When G factor will be different for the lower state and G factor is different from the upper state, then of course the number or then of course the splitting gap between the lines in the lower state will be different from the splitting lines from the splitting gap between the upper state. And due to that one, because the G factor will be different for the lower states and for the upper states, and due to that one, the number of lines will be greater in number. And that's why we have the anomalous Zeeman effect. So the two terms have different G factors. And here the two terms mean that we are talking about the ground state term, for example, or the excited state, or we are talking about two excited states. One is the lower excited state and the other is the upper excited states. And the terms related with those excited states here are being referred as two terms. So the two terms have different G factors because the relative contributions of spin and orbital magnetism to the two states are different. So you see that again, here the point is that the contribution of the orbital of the spin magnetism and the orbital magnetism to the two states are different. So their contributions are different. So we have different values of J for the two states. And you know that capital J, which is called the total angular momentum of the atom, is determined by the spin angular momentum and by the orbital angular momentum L. You see that when we are dealing with single atoms, you can use small letter for S and small letter for L. But when two or more than two electrons are involved and we are dealing with such vectors, then we need to use capital S for the spin angular momentum and capital L for the orbital angular momentum. And of course, capital G will then be used to stand at the total angular momentum of the atom. And you know that we have seen in the previous lectures that the total angular momentum J is actually the vectorial sum of the spin angular momentum capital S and the orbital magnetic and the orbital angular momentum capital S. Capital L. And similarly, for their corresponding quantities in terms of magnetic moments, the mu J, which is the total magnetic moment of the atom, will be equal to the sum of the spin magnetic moment mu S and the orbital magnetic moment mu L. So Gj is determined by capital J. So you see that we shall determine capital J, and with the help of capital J, we can determine the value of this Gj. This Gj is actually the Lande G factor, or we can say that it is the Lande G factor for the total angular for the total angular momentum of the system, which is capital J. And these things will be explained in the next few pages. Splitting in the ground state and the excited states are thus different because the Gj values will be different for both of these splittings. That is, the Gj will be different for the ground state and Gj will be different for the excited states. That's why the splitting will be different, which means that the splitting gap will be different. And the number of splitting lines can also be different, as we shall see in the next few pages. Though they are the same, That is, if we are talking about the ground level, for example, if there are more than two levels, then the splitting will be the same for all these levels. And for example, if we consider the excited level, excited state, and suppose that there are 5 levels in the excited state, then all these 5 levels will have the same splitting. But those splittings in the excited state could be different from the splitting of the ground state. But with itself, that is, the excited state will have the same splitting, and the ground state with itself have the same splitting. So this is what I am going to explain over here. Though they are the same, though they have the same splitting in the ground state and for the same splitting in the excited state, this produces a large number of spectral lines. So you know that in the anomalous we have more number of spectral lines in comparison with the ordinary Zeeman effect. So that's why in the beginning it was called anomalous Zeeman effect, and you see that I have given the reason for that one. The reason is that the splitting space between the ground levels and the splitting space between the levels corresponding to the excited states are different due to different values of Gj. And this Gj value is different because the J value could be different. And this J value is different because the spin magnetism and the orbital magnetism are different for the ground states and for the excited states. The effect is due to strong spin orbit coupling. So in the anomalous effect, since both spin magnetism and orbital magnetism are present, and there is a strong coupling between them, and you know that that coupling is referred to as spin orbit coupling, and such splittings is called spin orbit splitting, where capital S and capital L combine to form capital J. Likewise, magnetic moments mu S and mu L combine to form mu J, where mu J is the total magnetic moment of the atom, mu S is the total spin magnetic moment of the atom, mu L is the total orbital magnetic moment of the atom. Because I am using a capital notations and capital subscripts, it means that I am talking about the atom which has at least 2 electrons as the valence electrons or more than 2 electrons. Spin and orbital magnetism have different gyromagnetic ratios. For example, look at the gyromagnetic ratios gamma S, which is defined as the ratio of magnitude of the spin magnetic moment divided by the spin angular momentum. And similarly, gamma L, which is the orbital gyromagnetic ratio, is equal to the magnitude of the orbital magnetic moment divided by the magnitude of the orbital angular momentum. And if you are dealing with more than 2 or more electrons, you can replace these quantities with their capital counterparts. So if I use these calculations with the smaller quantities or with the capital letters, you should consider that both are actually the same things. Only the difference will be that the capital S will be actually the sum of all the spin angular momentum of the different electrons, and capital L means that we are adding the vectorial addition of the angular momentum related with the different electrons. And the same case is true for mu S and mu L. Okay, you see that in equation number 31 and 32, I have defined gamma S, which is the spin gyromagnetic ratio, and gamma L, which is the orbital gyromagnetic ratio. These quantities I have talked about many times in the previous lectures. Thus, corresponding G factors are different. And you know that the G factors are related with the gyromagnetic ratios through these relationships given in equation number 33 and given in equation number 34. So Gs is equal to gamma S times H bar over mu B, where mu B is the Bohr magneton, and similarly Gl is equal to gamma L into H bar over mu B as shown in equation number 34, and gamma L is actually the Lande G factor due to orbital magnetism, and the Gs is actually the Lande G factor due to spin magnetism. Now let's calculate the ratio of gamma S to gamma L. So using equation number 31 and 32, I am plugging in the values of gamma S and gamma L, and then you see that I have this expression. So this expression can be arranged in the following form. That is, in the third step, we have the absolute value of mu S divided by the absolute value of capital S, and then we have the absolute value of orbital angular momentum divided by the absolute value of the orbital magnetic moment. And then you see that I can rearrange these ratios that that is the absolute value of angular momentum to the absolute value of spin angular momentum, and then multiplied by a factor which gives you the ratio of the spin magnetic moment to the orbital magnetic moment of the atom. So I can also rearrange this in another form, that is the ratio of L mod to the S mod and the ratio of mu L mod to the mu S mod. And you see that this ratio is not being cancelled. That is, the denominator is not cancelling the numerator. It means that this quantity is not equal to 1. So we can say that the ratio of gamma S to gamma L is not equal to 1. It means that gamma S and gamma L are different quantities. That is the gyromagnetic ratio for the case of spin, and the gyromagnetic ratio for the case of orbital angular for the case of orbital magnetism. These have different values because their ratio is not equal to 1, as obvious in equation number 35. So here we can state that the ratio of orbital angular momentum, magnitude of the orbital angular momentum to the magnitude of the spin angular momentum is different from the ratio of the orbital magnetic moment to the magnitude of the spin magnetic moment. That is why J does not coincide with mu J in the line of action. That is, there is a non-zero angle between J and minus mu J. You see that in one of the previous lectures, we have seen that the orbital angular momentum L and the magnetic moment mu L are oppositely directed, that is, they are anti-parallel to each other. And similarly, we have also seen that the spin angular momentum S and the spin magnetic moment mu S, they were also anti-parallel to each other. But you know that due to their ratios are not equal, and the ratio of gamma S and gamma L is not equal to 1, which means that the angular momentum J is not anti-parallel with the minus with the minus times the with the total angular moment total magnetic moment mu J of the atom, that is capital J and minus mu J are not anti-parallel. There is a small angle between them. Now here I am going to discuss the diagram. This is the diagram in which we have applied the magnetic field to the atom. So first of all, I shall talk about the upper part of this figure. You can see I have the spin angular momentum, which is shown by capital S. I have the orbital angular momentum shown by capital L. And you know that I have added capital L and capital S by head to tail rule, because these two are vector quantities. And the sum of vector quantities of capital S and capital L will give you capital J. Capital J is the vectorial sum of capital S and capital L. So this is the total angular momentum of the atom. So the total angular momentum of the atom is represented by capital J, and it is the vectorial sum of the orbital angular momentum and the spin angular momentum. So capital J is shown over here. So you see that when magnetic field is applied, this capital J can have any direction. Its direction is not fixed when there is no magnetic field. But when you apply magnetic field to an atom, for example, in this case, we are representing the magnetic field by B naught in the Z direction, then of course the vector J, which is the total angular momentum of the atom, will carry out its precessional motion about the magnetic field B naught. So J will carry out a precessional motion about the magnetic field B naught. in the form of this loop. That is, the tip of the vector j will trace out this loop and will keep on tracing this loop. This is called a precessional motion. And you know that this vector j has three components, jx, jy, and jz. Due to the precessional motion, the two components jx and jy are averaged to zero, and only one component, which is the jz component, will survive. And this jz component is actually the projection of a vector j onto the z in the z direction or onto the direction of the magnetic field B naught. Now there is one more important thing in this figure is that look at the vector S, that is the spin angular momentum. This spin angular momentum carries out its precessional motion. You see that you can see the loop over here, that the tip of vector S traces out this loop. It means that the vector S, which is the spin angular momentum, carries out a precessional motion about the vector J, about the total angular momentum J of the atom. And look at the capital L, which is the orbital angular momentum, and look at its tip. Its tip also traces out a loop over here. And you know that this loop indicates, that is the red loop indicates that the angular momentum, orbital angular momentum, also carries out a precessional motion about the total angular momentum J of the atom. But you know that this J, the tip of the vector j traces out a green loop, which means that the vector j carries out a precessional motion about the magnetic field B naught. So in this case, when both spin angular momentum and the orbital angular momentum are present, the total angular momentum J of the atom or of the electron will carry out its precessional motion about the magnetic field B naught, and only its Z component, which is denoted by Jz, will be a measurable quantity, both experimentally and also can be estimated theoretically. Now let me talk about the lower part of this figure. And you know that in the lower part, I have mu s, which is anti-parallel to the angular momentum s. It has mu s has opposite direction to that of s, and the magnitude of mu s could be different from that of the magnitude of the spin angular momentum capital S. Similarly, you can notice down mu l. Mu L is oppositely directed to the angular momentum capital L. So mu L has the opposite direction. So you can say that mu L is anti-parallel to capital L. And here you can notice that mu S, the tip of the mu S vector traces out a loop, which is shown in blue line over blue loop over here. And you know that mu S traces out a loop. The center of this loop is actually mu jj. I shall be talking about mu jj in a few minutes later, but remember that mu s will carry out a precessional motion about the vector mu jj. Now similarly, look at the tip of the vector mu l, which is the orbital magnetic moment mu l. Its tip also traces out a red loop, and it means that mu l also carries out a precessional motion, but this carries out a precessional motion about the vector which is passing through its center, and this vector is mu jj. Now let me talk about another vector which is mu j. So you see that in the previous page I have said that mu j is not anti-parallel with j. That is mu j and that is vector j and mu j are not anti-parallel. They are oppositely directed, but they are not anti-parallel. Like the case in which mu s is exactly anti-parallel to capital S and mu l is exactly anti-parallel to capital S. In that sense, mu j is oppositely directed, but it is not anti-parallel to j, but it is slightly shifted at some angle. So this mu j also, you know that traces it's the tip of the vector mu j, which is the total magnetic moment of the atom, carries out a precessional motion in the form of a green loop. And this loop, you know that is again centered about this vector, which is mu jj. Now, what is mu jj? Mu jj is actually the jth component of this mu j vector along the direction opposite to the j vector. You know that this mu jj is actually in the say is xj is actually exactly anti-parallel to the vector j. So you can notice that this j vector and the mu jj vector are exactly anti-parallel to each other, whereas mu j is slightly different is slightly shifted from being anti-parallel. So this mu j carries out a precessional motion about a vector which is anti-parallel to the vector j, and that vector is what we call as mu jj. In principle, mu j, the projection of this mu j onto the vector which is anti-parallel to vector j is referred to as mu jj. So mu jj is the jth component of mu j in the direction of the direction which is anti-parallel to the vector j. And this, so let me summarize. Mu s will carry out a precessional motion about mu jj. Mu l will carry out a precessional motion about mu jj, and mu j will also carry out a precessional motion about mu jj. And what is mu jj? Mu jj is the jth component or the projection of mu j onto the direction which is anti-parallel to the j vector. So this is j vector, and this mu jj is exactly anti-parallel to the j vector. So you see that this is why. Now what will happen to the mu jj? Actually, this mu jj will also carry out a precessional motion about what? About the applied magnetic field. And you know that you can notice down the direction of the applied magnetic field over here. This is the direction of the applied magnetic field. This is B not positive. And you know that B not negative will be exactly downward over here. So this mu jj will also carry out a precessional motion about the applied magnetic field B naught, but will precess about minus B naught. This mu jj will also carry out a precessional motion, but very slowly about the minus B naught. So let's calculate the component of this mu jj in the direction of the applied magnetic field, which you may call as the z component. And in order to calculate that one, you need to use this figure. So actually, this figure is actually contains a simplified part of the figure on the left. Here you can see that you have a B naught. The direction of the applied magnetic field is also referred to as the direction z direction, and jz is the z component of vector j, where vector j is the total angular momentum of the atom. And now the bottom part of this one is, you see that this is mu jj. This mu jj is the same thing as I have shown in the figure on the left hand side. And if you want to calculate this mu jj, you know that this is mu j is I have shown, and this mu j is not exactly anti-parallel to the vector j. It is slightly shifted from being anti-parallel. The anti-parallel component is mu jj. And in order to calculate the component of mu jj in the direction anti-parallel to the vector j, the component will be referred as mu jj. And mu jj will be equal to the magnitude of mu j, which is mu j mod, multiplied by the cos of angle between mu j and j. So the angle, cos of angle between mu j and either minus j or simply j, because both will have the same angle, because cos of minus is the same as cos of plus. So either you take the angle as cos of mu j comma minus j, or cos of mu j comma j, both will be the same. So you see that I have shown the calculation of mu jj, which is actually the projection of the mu j vector onto the line which is anti-parallel to the j vector. So mu jj is equal to the mod of mu j into cos of the angle between mu j and j. Now I have to take the projection of this mu jj onto the direction onto the direction which is minus b naught, that is anti-parallel to b naught. or opposite direction to the applied magnetic field B naught or the negative B naught direction. So in order to calculate that one, that will be referred to as the mu j comma z, because it is the z component, or the z component means it is the component in the direction of the z component, in the direction of z axis, or in the direction of the magnetic field B naught. So mu jj, the z component of that one, will be equal to this vector mu jj multiplied by the cos of the angle between them, between the j vector and the magnetic field B naught. So you see that this will give you mu j, that is the z component of mu jj, and the calculation is shown over here. So you see that I have shown you the calculation of mu jj, which will carry out a precessional motion very slowly about the magnetic field B naught, and the component of the mu jj in the direction of the field will be referred to as mu jj comma z, that is the z component of mu jj, and its value is given over here. That is the projection of that one along the B naught direction, which is mu jj into cos of j comma B naught. So let me go through the text, relevant text over here. Only the component of mu jj in the z direction is observable. And you know that the z component of this one, which I have just talked about, is mu jj comma z, which I have shown this component mu jj comma z, that is the z component of mu jj. Only this component is observable because it is along the direction of the magnetic field. So only the component of mu jj in the z direction is observable. The projection of mu jj on the magnetic field B naught is calculated using the Lande G factor. So we can use the Lande G factor approach in order to calculate the z component of mu jj. And you know that mu jj is actually the projection of mu j onto minus j direction. This is what I have explained. So mu j precesses rapidly about minus j, and its projection in the minus j direction, which we call as mu jj, precesses slowly about minus b naught because of the weak interaction between mu jj and b naught. That's why the precessional motion will be slow of the mu jj about b naught. And its component is what we have calculated, which is z component of mu jj. And this is the only component that is observable. For the ordinary Zeeman effect, the spin magnetism is zero. That is, both spin angular momentum and spin magnetic moment are zero. And of course, the mu j, which is the total magnetic moment of the atom, will be determined by only the orbital magnetic moment of the atom. And mu j will be equal to mu L, and capital J and minus mu j coincides. In case of ordinary Zeeman effect, J and minus mu J both coincides. But in case of anomalous Zeeman effect, as we have discussed, J and mu J will not coincide. That's why there is a small angle between them. And due to small angle between J and mu J, they are not anti-parallel to each other, and that's why we have calculated the projection of a mu j in a direction which is anti-parallel to j, and that projection is labeled as mu jj. And this mu jj precesses slowly about the magnetic field B naught, so we need to calculate its z component, which is referred to as the z component of mu jj. So this component can be calculated. Here I present the sodium D1 line as an example of the anomalous Zeeman effect. So let's consider the anomalous Zeeman effect for the case of sodium D1 line. Before that, we have calculated that the ground state of the sodium atom is 2s half, and the first excited state has two levels. One of the levels is 2p 1 half. So you see that you can see that the spacing between, there are two levels corresponding to S1 half, because the 1s half is the value of total capital J. So capital J is equal to 1 half. And you know that when J is known, Mj, which is the magnetic moment, which is the magnetic quantum number, will be equal to plus minus half. So this is the value of capital J. Capital J is equal to 1 half, and the values of Mj will be equal to plus minus half. That is, the spacing between them is 1 between these two levels. Now consider the P state. For the P state, the value of the total angular momentum J is again 1 half. And again the levels will be Mj, there will be two levels, because there will be two possible values of Mj. When the capital value is J is equal to 1 half, the Mj values will be equal to plus minus half. Because you see that the difference with which Mj value will change will be equal to 1. So minus half to plus half is one value. But you know that the spacing between these two levels is smaller in comparison with the spacing between the two levels of the ground state. The reason for that, the Gj value, that is the Lande G factor for this upper state, is equal to 2 by 3. So you need to multiply this Lande G factor with these Mj values to get this Mj into Gj. So Mj Gj, which is the separation, which will give you the separation between these two levels, will be equal to plus 1 by 3 and minus 1 by 3. And to obtain this plus 1 by 3 and minus 1 by 3, you need to multiply this Mj value with the Gj, which is equal to 2 by 3. So the value of Lande G factor for this state, for this upper state, that is for the 2p half state, is 2 by 3. What is the value of Lande G factor for this case? The value is 2, because if you multiply 1 half by 2, you will get plus 1 half. You get, sorry, 1 half plus half. And if you multiplied minus 1 half by 2, you will get minus half. So the value of Gj for the ground state, that is for the 2s half state, the value of Gj is equal to 2, whereas the value of Gj for P1 half is 2 by 3. So the value of Gj for the two cases is different. That's why the splitting between them is different. For example, the splitting between these two levels in terms of Mj and Gj values is equal to 2, whereas the values for this one is 2 by 3. Now you see that, let's carry out the possible transitions. The possible transitions is what I have shown. Two red lines and two green lines have been used to show the possible transitions. And you know that the transitions must follow the rule that delta Mj should be equal to 0 plus minus 1. Other values are not optically permitted. So I have drawn these four lines following the rule that delta Mj should either be equal to 0 or plus 1 or minus 1. And I have shown these lines, and these are only the four possible lines. And all these four possible lines will have four different wavelengths. And you know that I have labeled them at the bottom, that two of them are pi lines, labeled by green lines are the pi lines, and the red lines are the sigma lines. Pi lines mean that in the pi lines the electric field is parallel to the magnetic field, and for the sigma lines the electric field is perpendicular to the magnetic field. All these four lines are linearly polarized lights. For the pi lights, the electric fields of these components are parallel to the magnetic field, and for the sigma components, the electric field is perpendicular to the magnetic field B0. So we shall measure four different wavelengths. So D1 lines will split into four transitions, because it is the case of anomalous Zeeman effect. And in the anomalous Zeeman effect, we shall observe four lines for the case of sodium D1 line. Now let's talk about the D2 line. You see that here I present the sodium D2 line as an example of the anomalous Zeeman effect. For the D2 line, I have calculated, that ground state is the same in both. For the D1 line and the D2 line, ground state is the same, which is the 2s half. D1 for the D1 line, the transition is from 2p half to 2s half. But for the D2 line, the transition is from 2p3 half to 2s1 half. And you know that, but in the presence of the magnetic field, this J level, which is equal to 3 by 2, and it is a single level, but when you apply the magnetic field, this single level will be split into mj levels. That is, the J degeneracy is lifted when the magnetic field is applied. So when you don't apply the magnetic field, you will get only a single line over here, and also a single line for the ground state. But when you apply the magnetic field, this J value, which is equal to 3 by 2, this J degeneracy is lifted, and we have mj values. And you know that mj values are equal to plus minus 3 by 2 plus minus half, because these values should differ by plus 1 or minus 1. And similarly, for Sj is equal to half, the possible values for Mj are plus minus half. So you see that for the case of the J is equal to 3 half, I have shown Mj values which are plus minus 3 half and plus minus 1 half. And you know that for the upper state level, the Gj factor, which is the Lande J factor, is 4 by 3. And you know that you can compare this one for the case of D1 line. For the upper state, the Lande G factor was 2 by 3. But here for this case, that is for the P3 half state, the Lande G factor is 3 by 4. 4 by 3. So you can multiply 4 by 3 with each of these mj values to get mj into gj values, which are shown on the leftmost sides as plus 6 by 3, plus 2 by 3, minus 2 by 3, and minus 6 by 3. And similarly for the ground states, I have shown as plus 1 and minus 1, because the Lande G factor for the lower state is 2. So you see that the spacing between these 4 lines for the upper state are equal, and the spacing between these between two lines for the ground states, of course, these if there are more spacing, of course, for the ground states they will be equal, but luckily there are only 2 levels. But you know that the spacing of these 2 levels is different from the spacing of the upper states, because of the anomalous Zeeman effect, in which the mj values, in which the total value of j, which is equal to 3 by 2, is splitted into mj values as plus minus 3 and plus minus half. Now you see that I have drawn the possible transitions, optical transitions between these levels, upper 4 levels and lower 2 levels. And I have shown these transitions, 2 in red, 2 in green, and 2 in light brown. 6 transitions are possible. Why 6? Because delta mj should be either equal to 0, or the permitted value should be 0, or plus 1, or minus 1. And following that one, I have shown these 6 lines, because these 2 green lines follow the delta mj is equal to 0, and this plus 1 follows the delta mj is equal to plus 1, and these 2 brown lines follow delta mj is equal to minus 1. So these are actually 6 lines, and these 6 lines have different wavelengths. So 6 wavelengths are emitted when for the case of sodium D2 line, under the application of the applied magnetic field, and I have labeled them as sigma sigma, pi pi, and sigma sigma again. You can label them the red lines can be labeled as sigma plus, and these brown lines can be labeled as sigma minus and sigma minus. But all these 6 wavelengths are different, and when all these are linearly polarized. These pi lines means that they are linearly polarized with the electric field parallel to the applied magnetic field B naught. And for the sigma lines, which means that they are linearly polarized, but their magnetic fields are perpendicular to the direction of the magnetic field. So you see that here I am talking about the transverse measurement of these lines. And you see that the transverse measurement and the longitudinal measurement is what I have discussed in one of the previous slides. So now what is the conclusion? The conclusion is that for the D1 lines splits into four components, and the D2 line splits up into 6 components. So that's why this was not in agreement with the ordinary Zeeman effect. That's why this effect was labeled as anomalous. Zeeman effect. Anomalous means abnormal. But you know that this is not abnormal case. It is the case because it incorporates both the spin magnetism and the orbital magnetism, whereas the ordinary Zeeman effect only incorporates orbital magnetism, because in that case the spin magnetism was 0. So you will see that the spacing will be different. Whereas in the ordinary Zeeman effect, the spacing will be the same for the upper states and for the lower states. Now consider the neutral sodium atom having atomic number Z is equal to 11. The electronic configuration of the sodium is 1s2, 2s2, 2p6 and 3s1. That is, there is only one valence electron, which is the 3s electron in the sodium atom. So the ground state of the sodium atom is 3s1. For this state, the orbital quantum number L is equal to 0 and the spin quantum number is half. You know that for a single electron, the spin quantum number is always half. And the total quantum number J is equal to the mod of L plus minus half, which is equal to 0 plus minus half is equal to half. Multiplicity, capital M is equal to 2s plus 1. So put the value of S is equal to half over here. You will notice that you get 2 over here. So multiplicity is 2, which means that there are 2 possible values of J. But only for this, for S electrons, as we have discussed in one of the previous lectures, that this is a particular case for the S electrons, that being multiplicity is 2, we only have one value of capital J, which is half. So the term can be labeled as 3 2s half. Now let's consider the first excited states of the sodium atom, in which the 3s electron will be moved to the p states. So we have 3p electron instead of the 3s electron, as far as the first excited states of the sodium atom is concerned, with the electronic configuration is given, which is 1s2, 2s2, 2p6 and 3p1. First excited state is 3p1. For this state, we can write orbital quantum number equal to 1, spin quantum number again is equal to half, because this is the case of single electron, and J is equal to mod of L plus minus half, which is 1 plus minus half, and the possible values is 3 half and 1 half. And the multiplicity is 2, because if you put the value of S is equal to half, the multiplicity is 2. So we have 2 states, 3 2p 3 half and 3 2p1 half. This 3 is actually the principal quantum number. The actual terms are 2p3 half and 2p1 half. So this is what we have shown, these 2 states over here. For the excited case, we have shown the states 2p1 half and 2p3 half, because the 2 possible states correspond to the value of 3p electron. So when the first excited state is in the 3p electron, we have 2 possible states for that one, and these 2 possible states are what we have shown. So from the transition from the 2p1 half to 2s half, that is for the D1 line, we have the 4 components, and for the transition from 2p3 half to 2s1 half, which is referred to as the D2 line, there were 6 components. So total of these are the 10 components. When the transition of this excited state from 3p to the ground state occurs, there will be actually 10 components, and I have explained that 10 components. And these 10 components are possible only when we have applied the external magnetic field to the atom. So when there is no magnetic field, we shall observe only one component for the D1 line and one component for the D2 line. But in the presence of the magnetic field, 4 components for the D1 line and 6 components for the D2 lines are observed. The magnetic potential energy of the atom in the presence of the applied magnetic field B naught can be written as Vmg is equal to minus times the dot product of mu Jj dot B naught. You know that mu Jj precesses about B naught, so the magnetic potential energy Vmg will be given by the dot product of these two quantities, which you can write as the mod of mu Jj times B naught times the cos of angle between J and B naught. So you can combine the magnitude of mu Jj and the angle cos of J comma B as the Z component of mu Jj and Z. So the Z component of mu Jj times B naught. So you can this mu Jj with the Z component has the simple form as Gj mu B and Mj. And this is what we have spoken earlier in one of the previous lectures. So the magnetic potential energy is equal to minus Gj, mu B and Mj multiplied by the magnetic field B naught. Because here we have used the substitution for the values of the Z component of mu Jj, where Mj values are 0, plus minus 1, plus minus 2, and so on up to plus minus J, provided J is an integer. But if J is not an integer, then we have the half values. For example, if the value of J is 3 by 2, then the Mj values will be plus minus 3 by 2 plus minus half, and 0 will not be included over there. 0 will only be included when the values change by integer values. That is when the J values are integer, then we have Mj will change as integer values. So 0 will include. So 0 plus minus 1 plus minus 2 and up to plus minus J. So the maximum value of Mj will be equal to capital J. That is, there are two J plus 1 values when J is an integer. So Mj values between two consecutive levels differ by plus minus 1. The actual separation between the two consecutive levels is determined by Gj, which is the Lande G factor. So I shall work out an expression for Gj. So you see that as you can see that the magnetic potential energy depends upon Gj and other quantities. The other quantities, for example, mu J could be constant and Mg will vary according to this rule. And so the main values will be determined by the magnetic field. Magnetic field is usually constant. So Gj will determine the separation. And you know that I have used the factor Gj over here. That is in the separation between these levels. To determine the separation between these levels, you will notice that Gj is present over here. And I have given the value of Gj to be equal to 4 over 3. But we don't know how to determine the value of Gj equal to 4 over 3. How to determine this? That is, we need to find out an expression for the value of Gj. So you see that delta E, which is the difference between the two levels, which is the Mj level and Mj minus 1 level, that is between the separation between two consecutive levels. Then that is given by Gj into mu B into B naught. Because in that case, Mj will be equal to 1, delta Mj. So if you use the difference will appear as a delta Mj, and the delta Mj, that is the difference between the two consecutive total magnetic quantum numbers will be equal to 1. So I have used 1 over here on the right hand side, and I have shown the energy gap between two consecutive Mj levels. So you see that for each level we have the value of angular momentum L, spin quantum number S, and then we determine the total quantum number G. So I have shown these two levels with the possibility of quantum numbers. So L1, S1, and J1 are the quantum numbers corresponding to the lower level, and L2, S2, J2 will be the quantum numbers corresponding to the upper level. So you see that here the capital the quantum number J is actually the total quantum number of the atom, which is obtained by combining the quantum numbers L2 and S2. That is the orbital quantum number, and the spin quantum number will combine to give you the total quantum number J of the atom. So experimentally found values for the Lande G factor are given. Gj is equal to 2 for the 2s half state, that is for the ground state for this of the sodium atom. The Gj value is equal to 2, and Gj is equal to 2 over 3 for the upper state, which is 2p half state, and Gj value is equal to 4 over 3 for the upper state, which is 2p3 half state. So you see that I have given these G values which were found experimentally. Now the question is that can we find an expression for the Gj, that is for the Lande G factor, to produce these Gj values? Is there any expression? Yes, the answer is yes. So let's in the next pages we are going to find out an expression for this. So for optical transitions, the selection rule is delta mj is equal to 0 plus minus 1, as we have explained. It yields 10 lines under the rule for the D1 line plus D2 lines from the sodium atom. The quantum numbers L, S, J can be determined empirically from the measurement of the Zeeman effect. So you see that from the number of lines in the Zeeman effect, we can also determine the value of orbital quantum number, spin quantum number, and the total quantum number of the atoms if we know the theory. So these can also be determined from the empirical measurements. Now the next thing that we are going to do is that we are going to see that how the measurement of Lande G factor for the anomalous Zeeman effect is given, or how we can find and what is the expression for the Lande G factor that we can theoretically find out the value of G, which also matches with that of the empirical calculations from the spectroscopic data. In the anomalous Zeeman splitting, Gj. So you see that here I am using a capital J. I shall be using the label as capital L and capital S because I am going to generalize it not for the single atom, but not for the atom having single valence electron, but for those atoms having more than one electrons. So in the anomalous Zeeman effect, the splitting Gj, that is the total Lande G factor, can have values different from the values for the case of the pure orbital magnetism and for the case of the pure spin magnetism. You know that Gj is equal to 1 for the pure orbital magnetism, and Gj has a value equal to 2 for the pure spin magnetism. These are what I have also discussed in one of the previous lectures. For an atom, the total magnetic moment of the atom, which is mu j, will be equal to mu L plus mu S. So mu j is given by the vectorial sum of the orbital magnetic moment and the spin magnetic moment. And we can get the final result, which is the total magnetic moment of the atom. So mu L and L are antiparallel, mu S and capital S are antiparallel, mu J and J are oppositely directed but not antiparallel. This is what I have also discussed in the previous pages. So you see that since mu j and j are oppositely directed, but they are not antiparallel, that's why the value of the Lande G factor will be different from state to state, as we have seen for the sodium D1 line and for the sodium D2 lines. Due to this, different values of G factor result due to the coupling of the spin orbit magnetism. Mu j precesses rapidly about j. This is what I have discussed. Only the time averaged component of mu j onto the minus j direction, that is mu jj, can be observed. But to observe that one, mu jj precesses in turn about the minus b naught, and its projection on the z axis, that is mu j, z component of mu jj, needs to be calculated through which the gj can be determined. So you see that first we need to find out an expression for the z component of the mu jj. Once this is determined, we can find out an expression for the value of gj. That is the total Lande G factor for the atom. For that one, I am going to discuss this figure. So you see that in this figure, let's talk about the top part of this figure above the zero reference point. You see that I have shown angular momentum L combined with the spin angular momentum S from by head to tail rule, and the total and the sum of these two quantities is the total angular momentum J of the atom. The angle gamma is the gamma between the spin angular momentum S and the total angular momentum J of the atom. Now let's talk about the lower part. Mu L is anti-parallel to L. It is anti-parallel to L, but it may have different magnitude. Similarly, S over here, the vector S, the mu S vector. This is the mu S vector, which is horizontally placed over here from this point, that is from this point to this point. This is the magnetic moment mu S, and you know that it is oppositely directed to the vector S over here. So this mu S over here, and I have shown two parts of this mu S over here, half mu S and half mu S, so that they are combined to give you total length of the vector equal to mu S. So I have shown vector L and its magnetic moment mu L in opposite direction. Similarly, the spin angular momentum and the spin magnetic moment in oppositely directed are also shown. But for the vector J, I have shown mu J, which is oppositely directed but not anti-parallel. So mu J is not anti-parallel to J. Now, the tip of the vector mu J will carry out a precessional motion. As you can see, this is the precessional motion in the form of this loop traced out by the tip of the vector mu J about the red line. And this red line is nothing but mu Jj, which we shall see later that this red line from O to C is actually a mu Jj vector. So draw this diagram for the calculation of mu Jj. And this mu Jj is the vector shown in the red line from O to C. So the magnitude of the vector Jjj is equal to the magnitude of the vector OC. And the diagram is not to scale. This diagram is just drawn to show you the concept, but the things are not to the scale. Because some vectors will be larger, some vectors will be smaller in size. So you see that we have to determine the vector. If I determine the length of the vector OC, it means that I would be able to calculate the magnitude of the JJ vector. So let me show you this through this simple diagram, that the magnitude of the JJJ will be equal to OA plus AB plus BC. This is what you can see from the diagram. That is, the length of the vector OC is equal to the length of the vector OA plus length of the vector AB plus length of the vector BC. So you see that I have to determine the value of the length of OA vector, the value of the length of the AB vector, the value of the length of the BC vector. And I shall use three right angle triangle. One right angle triangle is OA and this dotted line. The other right angle triangle is A dotted line, and then from this dotted line to vector B. And the third right angle triangle is from B to C, and then following the dotted line. These are three right angle triangle. And using these three right angle triangle, I have written down these values. That is the projection of mu L with the cos of the angle between L and J, and then half of the magnitude of mu S vector multiplied by the cos of the angle between capital S and J. And for the third triangle, I have half multiplied by the mod of mu S multiplied by the cos of S and mu J. So you see that I have respectively used three right angle triangles. This is the first triangle. This is the second triangle, right angle triangle. And this is the third right angle triangle. So I have used these three right angle triangles to calculate the projections of vectors, for example, mu L with this one, and then I have calculated the other one. You can see from the figure that it is easily understood. Now you see that this half mu s into cos of sj is repeated twice. You can add them together, and then we have two terms in the third step. Here you can put the value of mu L, which I have shown over here. Mu L is equal to minus GL into mu B into vector L over H bar. And similarly, the magnitude, the mu S vector is substituted over here, which is minus GS into mu B into capital S over H bar. These vectors, these values I have calculated in one of the previous slides. Now you see that you can take some of the quantities outside the magnitude sign, and since I am going to take the magnitude, the negative signs will disappear. So I have GL mu B into the mod of vector L over H bar, and then the cos of this quantity. And similarly, the second term is plus GS into mu B into the magnitude of the vector S divided by H bar into cos of S comma J. And you know that the magnitude of the vector L is given by, as I have shown over here, the magnitude of the vector L is equal in terms of the quantum numbers is the square root of L into L plus 1 into H bar, where L, capital L, in the square root sign are the quantum numbers, and on the left hand side we have the angular momentum. Similarly, the magnitude of the spin angular momentum is equal to the square root of S into S plus 1, and outside that one we have H bar. This capital S is equal to the total spin quantum number. And then we have the magnitude of the capital J is equal to the square root of J into J plus 1, where this J, capital J, under the square root sign is actually the total quantum number, whereas the capital J, mod of capital J on the left hand side is actually the magnitude of the angular momentum. So the magnitude of angular momentum has been given related with the respective quantum numbers through the reduced Planck's constant. So substituting the value of capital N and capital S in these expressions, so I have written this expression over here. And then you can find out I have also substituted the values of G over there. For example, the value of GL is equal to 1 and the value of GS is equal to 2. And I have substituted the value of mod of capital L and mod of capital S over here. So the final result is that I can take mu B as a common factor, and then I have within the square bracket as a square root of L into L plus 1 multiplied by cos of L comma J, and then plus 2 times the square root of S into S plus 1 times cos of S comma J outside the square root. So you see that this is the final result giving you the magnitude of the mu JJ. Now you see that I need to calculate these quantities. That is, I have to substitute the value of cos of L comma J and the cos of S comma J. I am going to use the direction cosines in respective triangles. And I have discussed the direction cosines in at two places in one of the previous lectures. So I am not going to discuss these direction cosines. So the direction cosines as cos of L comma J is equal to the absolute square of S minus the absolute square of J minus the absolute square of L divided by 2 into magnitude of J into magnitude of L. And similarly for the cos of L comma J, the expression is the square of L minus the square root of J, minus the square of absolute value of J and minus the square root of absolute value of capital S divided by 2 into J into S. So substituting the values of these cos values in the previous expression, that is in this expression, putting the values of cos of L comma j and cos of S comma j, and obtaining these, we have obtained these values of cosines using the direction cosines, and substituting these values over here and simplifying the result. I have obtained the value of mu jj is equal to 3 times of j into j plus 1 plus s into s plus 1 minus l into s l plus 1 divided by 2 times the square root of j into j plus 1, and then this whole expression multiplied by mu b, where mu b is the Bohr magneton. And you know that on the left hand side, all these quantities, that is the j quantity, the s quantity, and the l quantity, are actually the quantum numbers, respectively the total quantum number, the total spin quantum number, the total orbital quantum number of the atom or of the electrons. But you know that the mod of mu jj is given by this expression, which is mod of mu gj multiplied by mu b multiplied by j vector divided by h bar. And this, since we are taking the mod of this one, so the negative sign will disappear, and we have the final result as gj into mu b into absolute value of a vector j divided by h bar. And the absolute value of a vector j can be used from this expression over here. And then, of course, the final result will be gj into the square root of j into j plus 1. Outside that one, I have a mu b. So I am using equation number 39 into equation number 34 into equation number 38. The final result, the final simplified result will be gj is equal to 1 plus j into j plus 1 plus s into s plus 1 minus l into l plus 1 divided by 2 times of j into j plus 1. So you see that this is the full expression for the total Lande G factor of an atom or of the electrons for a given state. So if any state is given, you can put the values of j, the value of capital S, the value of capital L, and you can find out the corresponding Lande G factor. For example, you can calculate the values of this Lande G factor for these states. For example, for the sodium D1 line, you can calculate Lande G factor Gj equal to 2 over 3 for this P half state. And similarly, for S half state, you will find Gj to be equal to 2. And for this P3 half state, you can find that this Jj is equal to 4 over 3. So putting the values from this data, you can find out the values of Gj for the corresponding terms. So you can find out that for the pure orbital case, Gj is equal to 1, because for the pure orbital magnetism, S is equal to 0, and Gj is equal to 2 for the case of a pure spin magnetism, where the quantities, angular quantities, orbital quantities will be equal to 0. But the true, these are the classical values. You know that the actual or more accurate value will be equal to 2.0023. This is the more accurate values. But you know that this value is very close to the actual classical values. So for fixed magnetism, that is when both orbital magnetism and spin magnetism are present, Gj takes different values. The energy between the levels of the sodium D lines is thus found using Jj into the following formula. So you can find out the energy separation between any two consecutive levels of the sodium D1 line and sodium D2 line, putting the corresponding values of Gj and the delta Mj values. For those values, you can find out the energy separation between any two levels of the sodium D1 line and sodium D2 line. So you see that in the today's lecture, I have discussed the anomalous Zeeman effect in much greater detail. But you see that the lecture is continued. That is the lecture, the next lecture. In the next lecture, we shall again consider another effect, which is called the push and back effect, in which again we shall apply the magnetic field to the atoms. So you see that this series of lectures, which is being covered under the slide number 13, are actually the lectures where we are considering the the application of the magnetic field to the atoms. So this is the end of slide number 13C for the course of atomic and molecular physics.